will take it again. It's, it's in.
I don't really look at that much. Maybe not all the classes.
It's in October. They're pretty well on that.
It's chemistry because
Who's your chemistry?
By the end of like everybody, my midterm wants to know what will go on. No, she just does it.
We have to do that, right?
Do I have to turn that?
You haven't done anything else,
I remember kind of like
you on Cal too.
you have to
Should be too soon.
you have to be cleared by your advisor first.
Mm-hmm.
Well, after everybody else. Well, I don't know.
Why can't I switch my semester for one?
I guess I really don't know.
That's so good.
Made it good.
I think everybody got almost.
Keep going to see.
But you know what I have to go back and retake? Chemistry math.
Sounds like a
I took it over the summer and I passed, but not enough.
We have to change the.
I had did.
I had it online. I would have missed it by I'm sick. It's the most awful foul.
Middle child.
Oh, I got a C. I just didn't get it. Fourth yet. Then, I don't know. I started grades
Do what?
Yeah, tell you where you are. Which is
Much attitude. It's, less than
fun. And just don't just I always thought it would take the sign language classes, but I never had the time available to take them. Well, I had it in high school. Find it.
I actually just got on the computer.
That's not good.
I know. Been 3 years ago.
Where are you from? They do a very similar thing here.
But you get through it fast. They just don't decide.
Yep.
That's why they only have to go. They have some. I
There's so many things wrong with that.
He's calling us a survey calculus. Yeah, it's open.
What's up?
Survey calculus.
Oh, Cal 2?
Yeah.
Listen, I'm
Got
in
the
Cal
Taylor
1
series.
right now.
Now, are you taking calculus 2 or survey calculus? Well, I have to take survey. Survey calculus is calculus. We call it a calculus.
I probably like
So that's probably what see how they're offering calculus 2 and 3.
I love how.
You want to do my derivative? I'm right here.
I have a calculator that does it for me.
Okay, I know.
No. I know how to do it. I can do that. I have that one. This is one I don't know how. Do this one. No.
24x
Here you go. No, this doesn't get turned in. Just for
Your email.
Oh,
I
yeah.
did get that one.
Okay, I figured you probably did. I'd check up on it. Get ready for your next trip again? Anybody else gonna pick you up? Just annual thing now. Have you heard back from Yale yet? When's that start? Pretty soon?
November 1st.
It's early enrollment.
like,
At least you know around Christmas time. That'll be exciting. You'll get it.
Oh, really? Yeah. Who else did I go? I know Emily did
You run a play, stuff like that.
It's on places.
You can do all the, which other Ivies did you like the best?
it doesn't matter.
Or black stuff.
Oh, just I guess her room was the best.
Okay. My daughter loved it.
There's other girls.
It's good stuff too. Yeah, small.
Like,
Oh, everything.
I have a
I'm too busy with work. I know. Actually, it's class.
I read that.
Oh, it is. Hey, that's the story.
But this works.
Right, it's the story that's.
Here.
Was it on the
But
syllabus?
I need to look that.
It wasn't on the syllabus.
There's me all of that.
What did Mary say?
It just, I don't know what it is.
Was she like freaking out?
She, that we know,
Yeah.
not just his fault. All our lots of things. He said something.
And we did a quiz, a 6-question quiz on derivatives.
Yeah. Which is so accurate.
Is it American or
Just everything all together.
Choose our history. She's in our.
She's like middle aged.
You sound so Oh, yeah.
And so, oh, you?
Oh, is that
Great.
That was me.
But,
You never answered that email, though, so maybe it wasn't.
I
said it like
yeah.
I said we're really overwhelmed.
Yeah. I don't know what else
That's it.
I was gonna
She just he asked us how we were, and she was like, I'm gonna be honest, I am so overwhelmed with our work, with what we're doing.
And
I
then
just
my
sit here and
Chris were like, coming up. Take a deep breath in, breathe out. And we
But that's it. We did it twice. We took
did it
two.
twice?
We took two. I haven't done this.
I'm thinking for this.
Yeah, I just don't think
This
an
is going to
idea
be
from-
my lesson for my niece. I have such a, oh my goodness. Oh my goodness. I have such a good, I have a couple different things to learn. I'll have like, the kids will have to figure out the correlation between height and shoe size, I would say. Like Shaq. Like
20 days.
And then I'm going to have 3 different options for like this week and shoes. And there's going to be something about aliens getting on a bus to go to Earth. Then another one's going to do something for aliens. But they're going to be like a small little story about them.
When we read our
Last night?
Yeah.
She said it was fun.
Yeah. So she said that 'cause we were basically all complaining about how our math teachers were like in our placement. Or not.
How sad, yeah.
We stopped pretty much. Like, yeah.
My
And so everybody pretty much agreed. And then she was like, you guys need to come and see me one day. 'Cause
Yeah.
she works at like the STEM department of her school. So she teaches first grade on Mondays,
Okay.
second grade on Tuesdays, third grade on Wednesdays, fourth grade on Thursdays, and fifth grade on Fridays.
Friday's birthday.
And so we're going in Friday. We're going to see if that can count for like 6
Are
hours.
you guys going to do this
or like
Friday?
7 hours.
No.
Okay,
Good.
Sometimes we have
I
nothing
know my
like
mom
that.
volunteered.
But hopefully we can like use that to count for our hours. And she said that we can miss the class. So we can do that and substitute like one of our classes.
All right, let's get started.
You can always have like a fun time. And
Have
she's
so
like,
much fun.
it's fun. She's like, my class is really cool.
Megan, here.
My favorite hard because
Elsa, here. Morgan,
Here.
Allison, here. Katie, here. Jessie, here. Leah,
Here.
Catherine,
Here.
Curtis,
Here.
John. Okay, so let me first finish that bonus question from last time. So we were able to determine A is the name, and so we can do the same way to determine what a B is. So what we did was to assume, because there's only 2 options, so A is either knight or knave. So I assume A is a knave. But if you say, what if I assume A is a knight? I got a contradiction right here, which tells me A is not a knight. A is a knave. But if you say, I did the other way, suppose A is a knave, you won't get any contradiction. If you don't get a contradiction, which means A is a knave. Okay. So similarly, I can do the same way. So B is a knight or a knave. So I don't know which one B is. I'm just going to assume A is night. And if you remember what, I'm sorry, B, not A. We're working on B. So B is a night. Let me plot the question. All right, so what B says A is a knave. Well, we already know A is a knave. This is confirmed. We already proved. A is a knave. Okay, so A is a knave. And what B says, if we assume B is a knight, then B tells the truth. B tells the truth. So what B says from the problem, it says B said A is a knave, and he did tell the truth. A is a knave. So which means there's no contradiction here, because B says B said, what did B say? B says A is a knave. So let me copy down the sentence so I don't have to look back and. This is what B says, and B tells the truth. And we already know A is a knave, so he is telling the truth. So that confirms that he is a knight. There is no contradiction because we don't have any contradiction. So B is a knight. But if you assume that B is a knave, you are going to get a contradiction, which tells you B is not knave and B is a knight. All right, so that was the bonus question, because the first part, when I did suppose A is a knight, there's sort of like an indirect proof. We got a contradiction, which means this assumption is false, or supposition is false, and then the other one has to be true. Okay, let's look at. So today we're going to talk about a new chapter, chapter 4, which is called mathematical induction. That is also a main technique in the proof of discrete mathematics, also in number theory. Chapter 4. Mathematical induction. Okay. We are also going to use a lot of algebra in this section. So you might have to refresh your memories about some of the formulas we learned in algebra class. First section we're going to look at is I'm going to talk about sequence. That's not the main thing, though. The main thing in this section, the main topic is mathematical induction. But a lot of questions involve sequence. The first type of question involve sequence. So that's why we're going to spend a little bit of time talking about sequence. If you had calculus 2, you should have learned sequence in that class. So what is a sequence? It's very easy. It's a list of numbers. So I may have the 1, 2, 3, 4, dot, dot, dot. So that's a sequence. But I may have 1, 4, 9, 16, dot, dot, dot. So I cannot list all of the numbers, so usually we use 3 dots to represent the other numbers. We omitted writing, but they still exist, following the same pattern. Okay, I can do, say, probably even fractions. 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. Each of them can be called a sequence. So one thing we are going to do is, if I ask you, let's say this is the first number. I'm trying to make for each sequence here, I'm going to make a chart. What we want to learn is to find out what we call the end term. If we think of this as the first number in the sequence, let's just call it the first number, and the second number, third number, fourth number, first number, second, third, and fourth, and so on. So if I ask you for the first sequence I have here, what is the 10th number? Can you tell me? The 10th number will be 10, right? What is the 10th number in the second sequence? Can you tell?
100.
100? How did you get 100?
Squaring 10.
Square root of 10, right? So it looks like you notice the pattern. It's every number, I guess, what is the pattern to say it specifically? What you said is correct. So 10 is the square of 10. But how did you know? So what the pattern is? The first number can be generated by what? We're doing squares, right? But we got to be very clear. We're doing the square of what number? The position in the sequence, right? Okay. So similarly, can you find what the 10th number is for the third sequence? What's the 10th number in the third sequence? 1 over the 10, right? Because you're always doing 1 divided by the position. So let me go ahead and make a chart here, kind of like in the textbook. So what I'm going to do is we have position in the sequence. Position. And we also have the number. Well, I guess we can just do mark. The number sequence. Position in the sequence and number in the sequence. So for the first one, for the first example, if it's 1, the number is 1. If it's 2, the number is 2. If the position is 3, the third number is 3. So we figure out the pattern will be, the pattern is, the number is in the sequence is always the same as the position, right? For the first example. So that's why I didn't have to do the others. I know the 10th number will be 10. So I can maybe put a first, first, second, third, and 10th. Now, what if I ask you, what's the nth number? The nth number in the sequence for the first one. What would it be? N, yes, good, okay. Because by looking at the first few numbers, first few terms, first 4 terms, we figure out the pattern. The number is always the same as the position for this example. So that's why I know, okay, if the position is n, if you ask me what an n term is, it's going to be the same, n. Now let's do another one for the second one. I'm going to do the same thing for the second one. The sequence, maybe I can put a sequence on top of it. 1, 2, 3, 4, dot. So in the second one, it's 1, 4, 9, 16, dot, dot, dot. We're doing chart here. And it's also the position and the number in the sequence. So the first number is 1. Second number is 4. The third number is 9. The fourth number is 16. So this time we figured out the pattern. Well, the 10th number is 100, which is 10 squared. The 100 here. So because we figured out the pattern, we noticed that the first number can be written as the position squared. Second number can also be written as position squared. Third number can also be written as position squared. So that's we figure out the pattern. the number is always equal to position squared. Position squared. So if I ask you what the nth number in this sequence is, it will be
N
n
squared.
squared. Yes, very good. Okay, now let's do, and this is actually we call it the general formula for this sequence, because if you have this, you are going to be able to determine every single number in the sequence. So if I ask you what is the 99th number, you do 99 squared, right? Replace the n with 99. Now let's work on the third one. I guess probably, well, you probably don't have to, let's not make a chart this time, I'll just ask you. So what is the nth term? What's the nth term in this sequence? 1 over n. Yes, good. So I'm going to put the general term right here. And this means, remember, this means the nth number in the sequence. Nth number and nth number, which looks like a algebra formula. Okay, but that can give you every single number in the sequence. All I have to do is replace that letter n with the position. If position is 1, I replace n with 1, with 1, with 1. If n is 2, I replace n with 2, 2, 2. 3, 3, 3, 3, so I can get the numbers I need. Okay, so that's the first thing. How to found a formula, or you can call it general formula. So in the textbook, you don't have to memorize this, but it's very straightforward. It's a general formula of the sequence. One of the homework question is the other way around. If I give you a formula, can you find out terms? So we can look at what I'm going to do will be on page 200. I give you a formula, a k. You can use k. What I just use is n. Most of the time we use n, but you can use k. I'm going to follow the textbook to use k this time. For all integers, k greater than or equal to 1. So that's ak. Now, so if I ask you to find the first 3 terms, let's say first 5 terms, find the first 5 terms of the sequence. First 5 terms. Okay, so what do I do? What's given is the general formula, like the one we have. We figured out. So previously, I gave you a list of numbers, asked you to figure out the formula. But this time, I gave you a formula directly. I want you to give me the sequence. How do I find? And again, they don't need you to list every single one, which we can't because there are infinite many of them. So we just need to get first 5 numbers. Plug in 1 to 5 into the formula, right? Replacing that k. As k, this time we use k to represent position, but you can use n. So I'm going to do a1. If I want to find 1, k equals 1, then I get a1 replacing that k right there with the number 1 if k equals 1. So I have 1 over 1 plus 1, that's 1/2. Similarly, I can do a2. If k is 2, then I replace k with 2. Now this is more like an algebra question. Looks like a function. a3, I replace k with 3. And a4, replace k with 4. So that's k equals 3, k equals 4. And if k equals 5, and I'm going to replace that k with 5. So 5 here, 5 on the top, 5 on the bottom. That's 5 over 6. Okay, so, and we can do one more. Look at another one. We're going to have another formula, b. And this time we use the letter, I'm going to use n this time. So n minus 1 over n. for integers n greater than or equal to 2. So which means if they say n is greater than or equal to 2, you don't have to do n equals 1. So we still do the first 5 terms. First 5 terms. So when n equals 2, notice that they told us to do n greater than or equal to 2. So you don't have to do n equals 1. When n equals 2, we replace that n with 2. So b2 equals this n, that n will be replaced by number 2. That 1/2. And if n equals 3, then b3 2/3. N equals 4, n equals 5, n equals 6. You need to find 5 numbers, 5 terms. 4 equals 4 minus 1 over 4. B5 equals 5 minus 1 over 5. And B6 equals 6 minus 1 over 6. Okay. And notice these two sequences, they are different. We found that the 5th term in both sequences, actually, they are equal to each other. So previously, we have this format. And if you compare, look, the first term is 1/2, the same. Second term, 2/3, the same. But for this sequence, it's still the first term. If you make a list of those numbers, first number, second number, third number, fourth number, they're exactly the same, although they have different formulas. Okay, but if you change the number you plug in this case, n k starts from 1, we plug it in. But over here, if we make n start from 2, you're going to get exactly the same sequence. But if n is 1, you plug it in. What do we get? If n equals 1, 0, right? 1 minus 1 is 0. 0 over 1 is 0. So if you make let n be 1, you're going to get a 0. So it has an extra number, but all the rest of the numbers are exactly the same. Okay. All right. So that just gives you an idea of what a sequence is. And in this section, we also talk about summation notation. If you had calculus 1, you should have learned that in that class. So the second thing we're going to talk about is summation notation. And most of the homework questions, because it's not the main thing for this section, we're going to be focusing on mathematical induction. So I don't want to spend too much time on the symbol summation notation. If you had learned statistics, we also use that symbol in that class. So for the homework question, in fact, I did not use summation notation. I just typed everything out, but we should still know what summation notation is. Sometimes, a lot of times, this makes writing much easier. So I just won't talk too much about this. Just kind of give you an example. So previously, we talked about those sequences. Go back to the 3 examples we had. The next thing we want to do is to add all the numbers in the sequence. So right now, a sequence, you don't do any operations. It's just going to be it's just a list of numbers. And first number, second number, third number. But if I want to add all of these numbers in the sequence, again, if you had a calculus 2, we have a name for this. We call it a series. But if you haven't had calculus 2, you probably don't know what that is. But that's what we are doing. We are adding all the numbers. So the first example would be 1 plus 2 plus 3 plus 4 plus ... plus the last number n. If I make this our last number. And be careful here. How many numbers do I have here in this sum? How many numbers am I adding in this? How many numbers?
N
Numbers, right? Okay. So I have those 3 dots there. It's different from writing. This is not the same as if I drop those 3 dots. If I get rid of these 3 dots right there, how many turns do I have here? How many turns? 1, 2, 3, 4, 5, right? Only 5 turns. I'm adding those numbers and n. But with those 3 dots there, it's not 5 terms. We have a bunch of them that have been omitted right here because I cannot write down every single one there. And the other reason is I don't know what n is. So when we add numbers, we could use the symbol. Anyway, if you had a calculus 1 or statistics, you should have seen the symbol in that class. What does this symbol mean, sigma? The sum, right? Yes, it means you take the sum. It's a capital letter for sigma in Greek letters. So we take, when in this question, we're doing addition. So that's when you can use sigma. When we use it, usually it's you are adding a bunch of numbers with a certain pattern there. So in this case, we only need to write down the formula, general formula. You don't have to write down all the previous numbers anymore. Just write down the last one. Because this symbol, summation, tells you to add all those numbers with this formula. But you have to specify, I'm sorry, I should use a different letter here. I'm going to use K. We already have N. I'm going to use K to represent a number. But K is going to go from 1 to N. Yes. So what does this mean? When I see summation, this symbol sigma, I know I should add. But what numbers am I adding? I'm adding K. But K does not represent one number because they tell us this K can change. K is a variable, like a function. So K, what values does K take? 1, 2, 3. This is first number for A. All the way to the last number, which is N. So this pretty much means the same. So if K equals 1, I get 1. If K equals 2, I get 2. If K equals 3, I get 3. If K equals 4, I get 4. And so on. All the way, if K equals N, then I get last one M. And this symbol tells me to add all of them. Okay, so if this is clear, maybe I can ask you to give me the summation notation for adding, if I want to add the second sequence. So what is this equal to using summation notation? K squared, and K goes from 1 to N, right? Right? Okay. So here I'm giving you the sum of numbers in the sequence and ask you to write it in summation notation. The next example I'm going to do is to give you a summation notation and ask you to write it, to expand it. So this is, we call it an expanded form. But like I said, because it's not the main topic in this section, I'm just going to, all the homework question, if you look at what I give you typed up, it's different from what textbook gives you. Textbook uses the summation notation, but I give you the expanded form. But still, I'm going to give you an example. If I give you summation notation, can you figure out what the expanded form is? Okay. When I see sigma, I know I need to add numbers. But what numbers do we add? The first one is to replacing. This is the number you are going to add. But that's just a general formula. In order to get the specific number, you have to plug in the numbers for I. Okay, I is the variable. So if I equals 0, what kind of numbers does I take? I takes numbers from 0 to n. They only specify the first number and last number, but you should remember I actually, this means I is 0, 1, 2, 3, dot, dot, all the way to the last one, n. Okay, so if I equals 0, what do I get? Plug into the formula. -1, I'm going to go ahead and just plug in numbers. You can simplify this later. So I'm replacing this variable I with 0. Now, if I equals 1, I would get -1 to the first, and then 1 plus 1. And if I equals 2, I replace I with 2. Because in number theory, you are going to do this again, the summation notation. So 1, 1, 2, 2. And plus, well, I can be many, many numbers, right? So I cannot write down every single one. So usually if you write down the first two or first three, don't just write down the first one, okay? Try to write down a few, 2 or 3. And that should be enough. And write down the last one. So what is the last term? If I equals n, replacing I with n, yes. And if you want, you can simplify some of these. -1 to the 0 is equal to, no. Any number raised to 0 is equal to 1, okay? Except 0 to 0. Usually 0 to 0 is undefined, but any other number raised to 0 is 1. 0 plus 1 is 1. -1 to the first is -1 over 2. And -1 squared is +1 over 3, and dot plus dot dot dot. The last one, without knowing what n is, we cannot simplify that, but the others can be simplified. The first few can be simplified. So that's how you convert between these two types of forms, summation form or the expanded form. Usually, summation form is easy to write. In a lot of formulas, we like to use the summation form. If you had statistics, that's the formula. That's why you see in the formula. Because it's just easy to write instead of writing this long expression. But when you actually do the problem, you probably still have to expand it to see what numbers we are adding. Because when you look at this, you may not know what numbers you're adding. After you expand them, you can have an idea. Okay, we're adding 1 over 1, and subtract 1/2, and plus 1/3, and then next one is -1/4, right? So you would know by plugging numbers. If you just look at the formula, it's really not very easy. It's not very easy to tell what numbers we're adding there. Okay, so again, that's just a short introduction of summation notation. If you're given a sum, you can write it in summation notation. Or if you're given summation notation before, you can expand it. All right, so now we can move to, there's one more thing I want to talk about before we move on to mathematical induction. So go back to that formula we had talked about here. We just talked about it here. So remember now, we talked about two separate things. At the beginning, I introduced the sequence. Remember, sequence is comma, comma, comma. It's just separate numbers, a list of numbers. But then I added them. Like I said, in calculus 2, we call this series. But if you don't want to bother to remember the name, we're adding a bunch of numbers. But I do want you to look at this. So let me give you, go back to look at this example. Whatever form you like. If you want expanded form, expanded form usually is better to when you actually do a problem. Not easy to write, but when you do the problem, it's easy for us to see. So I want to ask you, if n equals 5, so this is the example we're looking at. I'm going to make a chart again. One column for n, another column for the sequence, not sequence, series, because we are adding them. Okay, if I ask you n equals 5, if n equals 5, n equals 5, can you tell me what this series become? What numbers we are adding? If n equals 5. Yes. Can everybody see this? Yes? It's a little different from the question I asked you before. When we had a sequence, if I ask you what's the 5th number, you just say, well, 5th number is 5. That's it, right? Without mentioning the previous numbers. But over here, we're talking about, this is not called a sequence anymore, we call it a series. We are adding a bunch of numbers. So we're adding the numbers from 1 to n. If n equals 5, it means you're adding numbers from 1 to 5. So one mistake I saw in the past, some students get confused by sequence and the series. They when n equals 5, they thought it's just the last number 5. That would be incorrect. You have to bring the numbers always start from 1 all the way to whatever the last number is. So this is your first number you are adding, and n is the last number we are adding. So first number is 1, last number is 5, and plus the numbers in the middle. I think everybody is clear about that. A tricky question is, what if n equals, maybe we should try one more before we try that one. So what if n equals 2? What numbers are we adding?
1 plus 2.
Yes, good. What if n equals 1?
Just 1.
Just 1, yes. Okay, be careful. Although I wrote down 1 plus 2 plus 3 plus 4 and dot, 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 you don't have to assume every time you will get those numbers. You're not going to always get 2, 3, 4. It really depends on what n is. If n is 5, yes, you're going to go from 1 all the way to 5. But if n is 2, you're only going to go from 1 to 2 because n represents the last number. So n, this means that's your last number. 2 is your last number. So you can only go from 1 to 2. If n equals 1, which means the first number is, you only got one number you are adding. So you're only going to have the first number. Okay, so be careful about that. Now, what if n equals k? What numbers are we adding? If n equals k, we're adding numbers from 1 to k, which will be plus k, right? So this time it's going to write down the first 3 numbers. Again, like I said, how many numbers first few turns you want to write, it's up to you. But usually at least write down 2, okay? We want to see a pattern. Okay, is everybody clear about this? When n equals k, we're adding numbers from 1 to k, right? So first, second, third, and all the way to k. Now, what if I make n equal k plus 1? The numbers we'll be adding are from 1 to, yes, the last number will be k plus 1. Remember, n is always the last number. So I'm going to add a 1 plus 2 plus 3 plus dot, dot, dot. And plus, save a little bit space here. We are usually, when you write down a series, adding numbers, you just need to write down the first 2 or 3 and the last one. You don't have to write down all the ones in the middle. You can omit them. But for this case, I want you to write down the last 2 instead of just the last one. So this is the last one. What if I want you to write down the last 2 numbers we're adding? K and k plus 1. Is that right? Okay. Because when n equals k plus 1, it means we're adding numbers from 1 to the last one. This is the last number, k plus 1. And the number right in front of it, right before it, is k, the previous one. So why do we want to do this? Because in the mathematical induction, we want you to write down the last 2 terms so you can compare, see what the difference is. And look at these 2 series. From when n goes from k to k plus 1, what's the change we have? It has an extra term, right? K plus 1. All the previous ones, they match. 1 plus 2 plus 3 plus 4, 5, 6, all the way to k, and then k plus 1. Okay, so we do want you to pay attention to that. Now let's do one more, and this time I think I'm going to do the cube power because the square is your homework. So I'm going to do the third power. If I want to add 1 cubed plus 2 cubed plus 3 cubed plus dot, dot, dot plus n cubed. And I'm going to ask you the similar questions. So n means the position. 1 cubed plus 2 cubed plus 3 dot, dot, dot plus n cubed. N equals 1. What is this? 1 cubed. Okay, so you are going to get 1 cubed. If you want to simplify it, you can. Equals 1. But we're going to do that later because right now I just want you to know how to get the formula or different n's. So if n equals 1, you're only going to get the first one, 1 cubed. What if n equals k? K cubed, right? It's actually very easy if n equals k. All you have to do is to replace the last n with k. Okay. Now, what if n equals k plus 1? And remember, I want you to write down the first 3 terms and the last 2 terms. We're adding. Yes, very good. Okay. Can everybody see this?
Yes.
All right, good. So the last one will be, because this time the numbers we're adding has this pattern, the position cubed. So the last position is k plus 1, you do cubed. But the previous one will be k cubed. Okay, so if you know all of these, we are ready. So this is just trying to help you understand the first type of mathematical induction question. Mathematical induction can be used to prove many different types of problems. We're going to look at 3 different types. One is like a formula like this. And the other is going to be divisibility problem, and the third one is inequality. So there will be 3 different types. Like I said, it can be applied to many other questions, but we're only going to look at those 3 types. And mathematical induction is also used a lot in the proofs. I know we don't have any math majors here, but I mean, the papers I published, I would say pretty much 60%, 70% of them I use mathematical induction, and I also use indirect proof. A lot of times you can combine them. So let's look at the first example. We're going to use the example to explain how mathematical induction works. So first example is the one we just talked about, this one. So I'm sure, well, I don't know if anybody just had a calculus 1. If you had a calculus 1, you should have seen this formula in your in the definite integral. Okay, so when you learn Riemann sum, you need to use this formula to try to find the definite integral. And also there's a formula 1 squared plus 2 squared plus 3 squared plus ... plus n squared equals 6n times n plus 1 times 2n plus 1. And there's also a formula for 1 cubed. 3 cubed plus ... plus n cubed equals. Well, there are 2 forms. I'm going to use this form. This one is your homework question. So what I'm going to do today is the first and the third. Okay, the first one and the third one. All right. So when we in calculus, you never need to prove this. We're just given the formula, say, okay, use it. Whenever you see 1 plus 2 plus 3 plus n, that's going to be equal to, you can replace it with n times n plus 1 over 2. And whenever you see this, you can replace it with that formula. And compare the left-hand side and right-hand side. The right-hand side is quicker. It's easier, quicker. So there was a story about mathematician Gauss. If you had a history of mathematics, you probably have learned about Gauss. There's a mathematician. But he told that story to the students, and we don't know whether it's true or not. But so he said when he was in, I guess, elementary school. So one time the teacher wanted to take a break, and so the teacher gave the students a problem to work on. that he asked the student to do 1 plus 2 plus 3, add all the numbers. Let's to, I forgot the last one. Let's just say to 50. So the teacher thought this will take the students quite a while to work on, so he could take a break. But only took Gauss a few minutes to figure it out. And so what he did actually is use this formula. But how did he figure out this formula? But without the formula, you have to do this way. 1 plus 2, 3. 3 plus 3, 6. 6 plus 4, 10. And you have to keep doing this. And it does take quite a while, right? But with this formula, you don't have to add 1 by 1 anymore. So how do I use the formula? Right, yes. So the last number, if I plug into the formula, this n, the last number n is 50. So I can just replace n with 50 on the right side formula. So n is 50, this n is 50, this n is 50. So 50 times 51 over 2. And that gives us 25 times 51. And you can get the answer, multiply them to get the answer immediately, right? Okay, so this is much quicker. It probably take you 1 minute, less than 1 minute. But if you did not know this formula, yes, you have to keep adding. That takes you probably quite a while. And so with this formula, you can add any number of, like first 100 numbers, first 200 numbers, first 1,000 numbers. All you have to do is replace the n with the 100, 200, 1,000. You can get the answer immediately. So this formula is very useful, but how do you know this is true? Like I said, in calculus, we're just told, okay, this is true, this is the formula, this is correct. But in this class, we're going to prove it, why this is correct. There are other ways you can do. For example, one way you could do is take the first number, add the last one. It's 1 plus 50 is 51, right? And 2 plus 49 is also 51. 3 plus 48 is 51. So it's a bunch of 51s. And 25 51s you could get. So that's one way you could do that. In general, we can prove that any even complicated ones like this by using mathematical induction. Okay, so first type of question is to prove the formulas that look like this. The left-hand side is sort of like a summation. It's adding a bunch of numbers with a certain pattern. Although, it's time-consuming if you want to do this way. So that's why it's better to have a single formula to do this type of question. But we do need to prove. Before you use them, we do need to prove they are equal to each other. So let's start with the first one. Well, I'm going to write down the problem again. So 1 plus 2 plus 3 plus dot, 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 plus n equals n times n plus 1 over 2. So how do we prove this? It looks like we only have one formula. But this formula represents infinitely many equations. Why? I showed you before, because this n is a variable. If n equals 1, you get 1. If n equals 2, you get 1 plus 2. If n equals 5, you get 1 plus 2 plus 3 plus 5. If n equals 50, you get 1 plus 2 plus 3 all the way to 50, right? So it's actually infinite many of them, because this n can change. So there's no way you can say, well, we usually do have to specify for integers greater than or equal to 1. So n starts from 1 all the way to infinity. And infinity is not a number that you can keep going on forever. So if I try to prove this way, say, let's plug a 1 in here, and 2 in here, and 3 in here, and 4 in here, 5, 6, 7, all the way, and verify every single one. For every single n, the left-hand side equals the right-hand side. You cannot do that, because there are infinite many cases, right? So what should we do? So we're only going to, with mathematical induction, you only need to do 2 steps instead of infinite many cases. So, step 1, we call it the basis step. The basis step is you always pick the first number for the position n and plug it into the formula you want to prove. since we're told n is greater than or equal to 1, so what is the first number for n? 1, right? So you got sometimes it's not always equal to 1. Sometimes they could start from 2. Then you would plug in 2. If n is greater than or equal to 5, then you plug in 5. Okay, so whatever they tell you there. So when n equals 1, can you plug, let's plug 1 into the left-hand side. So what would be the left-hand side if n equals 1? It's just 1, right? That's why I asked you those questions there. If n equals 1, you only get 1. Although it looks really long, the left-hand side, but when n equals 1, the left-hand side is just going to be one number, 1. Okay. Now, what about the right-hand side? Let's work out the right-hand side. Replace n with 1. 1 times 1 plus 1 over 2, which is 2 over 2. That is equal to 1. And notice that left-hand side does equal right-hand side because they're both equal to 1. So what does this tell me? What did I just prove? This formula is true for what? N equal to 1. Am I done? No, because we're supposed to prove this formula is true for all integers, 2, 3, 4, 5, 6, 7. But we cannot keep doing this forever. So what we're going to do is called, the next step is called inductive step. So the inductive step, this is something you kind of have to, at the beginning, you would just memorize it, okay? Imitate how we do this. Later, I will explain why we do this way, but I think after some exercise, you should have a better understanding of why we're doing those. So you will always assume this formula, whatever they ask you to prove, is true for n equal to k. The first thing you always say, assume the formula, in this case, the equation, part of formula, is true for n equal to k. You always assume that. And what is the formula if n equals k? Yes, good. All right, so James said the formula is 1 plus 2 plus 3 plus dot dot plus k equals k times k plus 1 over 2. So that is something I asked before. The left-hand side, if n equals k, the left-hand side would just be 1 plus 2 all the way to k, the last number k. The right-hand side, you will replace n with k. So that's how I got this formula. So this one is your assumption, which means you already know this is true, okay? So that's something we already know. We know when I add numbers from 1 to k, it's going to be equal to this, k times k plus 1 over 2. But we are going to use this to prove, I think you're going to have to save like 3 or 4 lines here. And so usually this is what I always do to write down our goal, what we need to prove. We assume, that one is assumption. We assume this formula is true. But we want to prove the formula is true for n equal to k plus 1. All right, if I want to prove the formula is true for n equal to k plus 1, I need to know what the formula is if n equals k plus 1. So what is the formula? Again, this is the formula we want to prove. And we just wrote down the formula if n equals k. But what if n equals k plus 1? What would this formula be? The left-hand side would be if n equals k plus 1. What would it be? Does everybody know?
It would be the same, but then you also add k plus 1 at the end after k.
Yes, that's right. So this is what we did before. If n equals k plus 1, the left-hand side will be that. Okay, let's go ahead and copy down that. Plus like I said, I want you to write down the last two terms. You don't have to, but it would be helpful if you write down the last two terms. So that's the left-hand side. What about the right-hand side? Replace that n with k plus 1, right? Okay, because that's what n is. I'm going to go ahead and simplify that. If I replace this n with k plus 1, what do I get? In the parentheses?
K plus 2.
Yes, good. Okay, so is everybody clear about these two formulas we have so far?
Yes.
Okay. So what you have to do in the inductive step, you will have to write down the formula for n equal to k. Left-hand side equals right-hand side. You also have to write down the formula for n equal to k plus 1. Left-hand side, right-hand side. You don't have to use a new variable k. You can keep n and n plus 1. But if this is the first time you're doing mathematical induction, where you are still not getting the idea of mathematical induction, it's better to use a different variable k instead of keeping n there. Later, after you fully understand mathematical induction, you really actually don't have to change n to k. I did it here for the usually at the beginning. So let's look at, here's what we need to prove now. It's kind of like saying, if I tell you 1 plus 2 plus 3 plus dot dot plus k equals, if you add the first k numbers, the formula is you would get k times k plus 1 over 2. Can you use that to prove adding the first k plus 1 numbers, you would get k plus 1 times k plus 2 over 2. So assume this is true to prove that is also true. I'm going to put a question mark here because we don't know whether adding the first k plus 1 numbers will give us that or not. Okay, so what should we do? Any idea how we prove the bottom one from that one? The second formula from the first formula here. You can compare them. Look. Just look at these two formulas we want to we have. That's one we given. That's the one we need to prove. So usually, if you want to get this one, usually you can compare one side of the equation. They look very similar. There's some differences. You can try to get the right-hand side first, but it's not very easy if you look. How do I get k plus 1 times k plus 2 over 2 from k times k plus 1? It's not very easy to do. So usually, we're going to start from the left-hand side for this type of question. How do we get 1 plus 2 plus 3 plus k plus 1 from 1 plus 2 plus k? How do we get this one from that one? What operation can I do to get the left-hand side I need from the left-hand side I have? Compare them. 1 plus 1 plus 2 plus 3 plus dot dot plus k. How do we get this from that? Add k plus 1, right?
Yeah.
Okay. So this is what I'm going to do. And in algebra, we know, let's quickly go over algebra question. If I have 3x minus 7 equals 2, how would you get x minus out? You can add 7 to both sides, right? When you add 7 to both sides, it's not going to change the equation. It's still going to be equal, right? But if you only add 7 to the left, of course, they're not going to be equal anymore. You cannot say 3x equals 2. But if you add 7 to both sides, they're still going to be equal. The same idea here. If we have an equation, I do have an equation right here. I can add both sides, add by k plus 1. That's what I'm going to do. So add k plus 1 to both sides. Add, well, I can just write add both sides by k plus 1. So what are we going to get now after we add k plus 1 to both sides? So copy the original left-hand side, copy all of that, and I'm going to add k plus 1 to the left-hand side. And remember, we should also add the same thing to the right-hand side to keep the equation. I'm going to use using the red color to show what I did. So the one in black is still the original formula for a equal to k. I decided to add k plus 1 to both sides. That would still keep it as an equation. And why did I do that again? Why did I add a plus 1? How did I know I should add k plus 1 to both sides? Because that's what I need to prove. In the formula that I need to prove, it has a k plus 1 there. So that's why I did that. Okay? So that's why usually it's helpful if you go all the way to the bottom or put this on your scratch paper so you know what to do. Otherwise, if you just look at this, you may not realize, okay, what I should do. What should I do next? But if you put down the formula, write down the formula somewhere for k plus 1 n equal to k plus 1, you can compare them. So, okay, looks like I'm missing a k plus 1, so I'm going to add k plus 1 to both sides. So now we can do algebra. The left-hand side already matches the left-hand side we have. So you don't have to do anything about it. Keep it. I can copy it one more time. Just copy this. The right-hand side, let's take a look, does not match the one I need to prove. I need this right-hand side, but what we have is something plus something. So that's algebra. How do we add fractions? I put a 1 down there, equal to denominator, right? What is the LCD for those two fractions? 2. So I'm going to multiply the second one, both top and bottom, by 2. So put a 2 here and 2 there. Now we have a common denominator 2. And add the numerators. There are two possible ways you could do. You could distribute, and combine like terms. If you do that, let's see what you're going to get. So if you add k times k plus 1 plus 2 times k plus 1, the top, you add this top and that top. If you distribute to get k squared plus k plus 2k plus 2. And you can combine like terms to get 3k plus 2. And this is a trinomial. So you're going to end up with something on the top like this. Still does not match what we need. This is what we need, right? So you have to do factoring. Does everybody know how to factor trinomial? Do I need to go over that? No? So that's from your algebra class. You factor this as k plus 1 times k plus 2, which matches what we need, right? That's one way to do the question. But sometimes this could be a little tedious if you have very complicated ones here. So usually I don't recommend that way. It's still correct if you like this way. The way I usually do will be, because all I need is that. I need to change the top to k plus 1 times k plus 2. So instead of multiplying everything out, I can go and do factoring later. I can go ahead and do factoring. Look at the top. Look at the top. They have a common factor, k plus 1. You all see that? So I can factor out a k plus 1. Factor this out, factor that out, and we have k plus 2. Well, that's exactly what we need. It's much faster, right? Okay, so you don't always have to multiply everything out and try to simplify it to get to do factoring later. You could just, if there's anything you can factor right now, go ahead and do that. So we're done. We proved that formula. Okay. Well, here we have about 15 minutes. I'm going to explain why this works. So look at what we just proved. So you may say, well, how did you prove everything? This formula holds for every integer. It looks like you only proved this formula holds for 1, and this formula holds for k plus 1. You did prove this formula holds for k plus 1. But that's it. How can you say you proved for everything? Okay, so let's look at these two steps here. using this example. That's the explanation. If you say, well, you don't have, when you do the problem, you don't have to give me the explanation. But I think if you understand this, that will help you understand why mathematical induction works. So in general, this is the formula we want to prove. You have infinite many formulas. So what we actually proved, what did we prove? We proved this formula holds for the formula for the first step. We proved the formula holds for n equal to 1. In the second step, we proved, what did we prove in the second step? Assume, which is a condition, if the formula holds for n equal to k, then we can prove the formula holds for n equal to k plus 1. Right? That's what we proved in the inductive step. So in the basis step, we proved the formula holds, or you can say the formula is true. The formula is true for n equal to 1. In the inductive step, we proved, this is what we proved. If the formula is true for n equal to k, then we can prove this formula is true for n equal to k plus 1. And notice this variable k right here. K is a variable. K can change. K can take any integer. So let's look at, have we proved the formula given? The formula given is true for every single integer. I guess I can make a chart here to show you that. So what did we prove? We proved that the formula is true for n equal to 1. So if n equals 1, the formula is proved. The formula is proved, right? Okay, now, have we proved the formula is true for n equal to 2? We didn't prove it directly. But based on the inductive step, what did we say? If the formula is true for n equal to k, then the formula is true for n equal to k plus 1. And combining the basis step and inductive step, we already proved that the formula is true for n equal to 1. Then, by the inductive step, the formula should be true for what? N equal to 1 plus 1, which is 2. Is that right? Yes? Okay. In the inductive step, we proved a very general property. It said if the formula is true for any k, n equal to k, any k, then the formula should also be true for k plus 1, any k plus 1. So if I pick a special number for k, which is 1, if the formula is true for 1, then the formula is true for 2. Right? So the formula for 2 is correct. What about 3? How did we prove the formula is true for n equal to 3? Because we already know the formula is true for 2, if n equal to 2. Using the inductive step again, if the formula is true for 2, then the conclusion says the formula is true for 2 plus 1, which is 3. Right? So for 3, that formula should be true. And why is the formula true for 4? For n equal to 4. The same thing, right? I just replaced that k with 4. And 4 implies 5. 5 implies 6. 6 implies 7. You see that? So that tells me I can keep going using this. K implies k plus 1. So if k is 1, implies 2. K is 2 implies 3. 3 implies 4. 4 implies 5. 5 implies 6. 6 implies 7. You can go on forever. Okay? Does that make sense? So this way, I have proved this formula is true for every single number. 1, 2, 3, 4, all the way to infinity. Okay. It's very similar to dominoes when you're playing. So when you set up dominoes, if you set it up very well, the first domino piece will push down the second will push down the third will push down the fourth, and suppose you have infinite many of them, you will push down every single one of them, right? So the basis step we proved is like the first one. you push down the first domino piece. And the inductive step is like you're setting them up very well, correctly, then you will guarantee, because what does the inductive step say? It says if you push down the kth domino piece, the kth domino piece will push down the k plus 1, the next one, right? The kth domino piece, suppose you have kth one here, you will push down the k plus 1 piece, the next piece. And k can take any integer. So if k is 1, the first one push down the second one. If k is 2, the second push down the third. If k is 3, the third one push down the fourth. So that tells you every single piece will be pushed down, right? Okay, so it's mathematical induction. The idea is very similar to playing like dominoes. Is everybody clear why this is correct? Okay. So whenever you do induction, at the beginning, you always try to probably imitate. There are always 2 steps to summarize. So you do the basic step, plug in whatever the number, the smallest number given. And you do inductive step. When you do inductive step, you always assume the formula is true for n equal to k and try to prove the formula is still true for n equal to k plus 1. So it goes from k to k plus 1. Because if you have that, it's like you're setting up domino pieces to guarantee, to make sure the kth one always, the kth domino piece can always push down the k plus 1 domino piece. If you can set up correctly, and yes, 1 push down 2, 2 push down 3, 3 push down 4. So it will push down every single piece. Okay. Let's take a second to look at the homework question. So I did give you example for 7 under section 4.1. So look at 4.2. Number 3 and 4. I don't think, let's see, I don't know if I have time to do another example, so I'd probably ask you to do number 3, number 4, and number 6 maybe. We can do 10 and 12 next week. But number 3 and number 4, they are asking you, number 3 and number 4, you don't have to do the whole proof. They are just trying to get you familiar with the steps. So write down the formula. So for example, number 3, they give us this formula. And they want you to write down the formula where n equals 1. So that's like doing the basis step. So write down left-hand side and right-hand side. And write down the formula where n equals k. Left-hand side, right-hand side. And write down the formula where n equals k plus 1. So all you have to do is that. And the last question, in a proof by mathematical induction that the formula holds for all integers, what must be shown in the inductive step? I can use the one I did to show you what you should say for this question. So again, number 3, number 4, you don't have to do the whole proof like I did. They are breaking down the mathematical induction into different steps so you can get familiar with the steps. Later you can do mathematical induction. So the first question, write down the formula for n equal to 1. So this is what you have to do. Okay, so n equals 1, what's the formula? The left-hand side is 1, the right-hand side is that. Okay, so that's the formula when n equals 1. N equal to k, which I already did right here, but I can do it one more time. So the left-hand side will be 1 plus 2 plus 3 dot 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 plus k. When n equals k, that's the left-hand side. The right-hand side replacing that letter n with k. And the third question is n equals k plus 1. So I write down the formula 1 plus 3 dot 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 plus k plus k plus 1. That's the left-hand side. The right-hand side equals replacing that n with the k plus 1. That's how you do the third question. The last question, you don't have to show me all the work there, like how you get that. All you have to say is, they're asking you, how do you how do you prove this formula from that formula? How do you use that formula for n equal to k to prove the formula for n equal to k plus 1? So all you have to say is, so what are you doing here? It's pretty much saying you need to prove that if 1 plus 2 plus dot dot plus k equals k times k plus 1 over 2, then 1 plus 2 plus dot 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 plus k plus 1 plus 1 times k plus 2. That's all you have to say. But how do you use this to prove that? For number 3, number 4, you don't have to show me that. Okay. So they want you to make sure how to do in that basis step. Question 1 is basis step. All of these are inductive step. In order to do inductive step, of course, inductive step is the major one, it's the difficult part. So they break down into steps. So first you need to write down the formula for n equal to k, and the formula for n equal to k plus 1. And then you prove if this formula is true, then that formula is true. Okay? So if they ask you, what do you need to show in inductive step? If this formula is true, then that formula is true. Okay? All you have to say is that. Okay? So we go back to the homework question. For number D, I don't need you to actually prove it like I did. How did I prove this formula? I added k plus 1 to both sides and using algebra, equal denominator vectoring. But you don't have to do that, okay? All you have to do is to just say, that's what I need to prove. That's for number 3, number 4. Number 6, you do have to show how to prove that. So like the work I did. Okay. So I will give you one that you have to actually do for number 6. If you have trouble, next Monday I can give you more examples. Okay? All right, so for number 6, you do have to do what I did, like follow my example. The basis step and inductive steps. You do have to figure out what you need to do. Usually it's adding. In this question, it's also adding. Why do you need to add for that homework question to get the left-hand side? Okay? All right, so I guess we can stop here for today.
Your meeting has ended.